Okay, so far dun sa chapter 3 natin, ang na-discuss natin ay yung 3.1 at saka 3.5. So tatapusin natin today yung 3.5. So sa 3.1, yung ating theorems mostly done by Euclid. So meron tayong ilan yung prime numbers na meron. So meron tayong infinitely many number of prime numbers. Of course, the natural question, follow-up question would be, how would we know paano tayo makakahanap ng prime number? Okay, so paano makakahanap ng prime number? Kaya sa 3.5, tinignan natin yung isang primality test, yung ating sieve of Eratosthenes. So sabi natin, yung ating sieve of Eratosthenes is an example of a deterministic primality test. So primality test kasi pag in-apply natin yung algorithm, we will know a deterministic primality test kasi pag in-apply natin yung ating primality test, sigurado tayo na itong listahan na to ay prime numbers, samantalang we have another list na sigurado tayo composite numbers naman. Okay? So, mamaya after natin i-discuss tong theorem 3.5.1, ay titingin tayo na example ng probabilistic primality test naman. So, yung ating theorem 3.5.1, sabi natin dati ay it's an improvement of the algorithm 1 kasi yung algorithm 1 ay brute force. Sasalain mo lahat ng multiples ng 1 to n kapag yung numbers mo ay 1 to n. Okay? So, dito sa 3.5.1, imbis na titignan mo yung multiples ng numbers 1 to n, kapag nilista mo yung numbers 1 to n, titingin ka lang hanggang sa square root ni n. So, we had an example last time nung naglista tayo ng integers from 1 to 200, imbis na kukuhanin natin lahat ng multiples ng numbers from 1 to 200, hanggang 13 lamang tayo. Okay, so ano ang multiples ng number 1 up to 13 only? Okay, so dahil yon, yung ating 200, the square root of 200, that's approximately 14 point something. Okay, ang sabi kasi sa theorem, kung composite number siya, lagi meron siyang prime divisor na mas maliit or equal sa square root of n. Okay, so, nabasa niyo ba yung proof? Meron ba kayong tanong sa proof? So, ang assumption natin, yung n natin ay composite. So, ang definition, ang consequence ng pagiging composite, it will have divisors other than 1 n itself. And so, it will have divisors, non-trivial divisors. So, dito, yung non-trivial divisors denote by a and b. Okay? So, of course, alam natin na one can be, between A and B, one can be greater than the other. So, let's suppose, without loss of generality, that A is not greater than B. Okay? So, of course, the case where yung B naman, yung mas maliit or equal sa A, will have a similar proof. Okay? So, kung si A mas maliit or equal kay B, sabi dito, sigurado ka daw na hindi pwedeng yung A ay mas malaki sa square root. Okay, so let's suppose otherwise. So dito sa part na to, let's suppose otherwise that A is greater than the square root of n. So kapag yung A ay mas malaki sa square root of n, so dito, dagdagan nyo, mas malaki siya sa square root of n. Yung B mas malaki kay A or equal kay A. So, ibig sabihin, si B din ay mas malaki sa square root of n. So, kaya dyan, the product of AB, it's greater than the greater than the square root of n times the square root of n. Eh, syempre, hindi naman pwedeng yung n mo mas malaki sa sarili niya. And so, it must not be true that A is greater than the square root of n. So, yung A mo, itong part na to, ay totoo. Yung A ay mas maliit sa square root of n. So, kung yung A Yung A ay non-trivial divisor ni N, yung A mo hindi pwedeng 1. Yung A hindi pwedeng 1. So, it must be greater than 1. So, sabi ng lemma 3.1.2, basta mas malaki sa 1, may prime divisor. So, specifically, si A dapat may prime divisor. So, pinangalanan na P yung kanyang prime divisor. So, we had a theorem last time. Lagi na natin ginagamit yung theorem 2.2.2. Isang item doon, ang sinasabi, basta divisor siya, basta positive divisor siya, mas maliit siya doon sa dinidivide niya. So, since P is the divisor, P is smaller in magnitude than A. Okay, so yung P ay smaller than A. Okay, so, yung ating P, it divides A, pero yung A divides N, and so by transitivity, P is also a divisor of N. Okay, so ibig sabihin, merong divisor na prime si N na mas maliit or equal sa square root of N. Okay, so bukod sa pag-apply sa sieve of Eratosthenes, saan pa pwedeng gamitin? So mag-shift ako ng sinishare kong screen. Dapat ang nakikita nyo na ay itong grid, meron tayong dots. Dapat yun ay nakikita nyo. So suppose we want to identify if 831 it's prime. Kung composite, may prime divisor siya na mas maliit sa square root niya. So ang gawin natin, let's get the contrapositive of this statement. So if Rn has no prime divisor, specifically prime, P, then N is prime. So, kung composite, dapat daw meron. So, kung wala, ibig sabihin, dapat yan ay prime. Okay, so gagamitin natin siya to test whether 831 it's prime. Okay, so kung meron tayong nakuhang divisor ni 831 na mas maliit sa square root of n, hindi natin mai-illustrate yung converse. Pero kung yung 831 after exhausting all of the prime numbers from 1 up to its square root pero wala pa rin nagde-divide, edi mai-illustrate natin yung contrapositive of theorem 3.5.1. Okay, so naiintindihan ba yung gagawin? So, ang mangyayari, kung hahanapin natin yung square root of 831, so ang square root ng 831, that's roughly 28. So, 28. So, kung ito ay composite, sabi dapat may prime divisor siya from 1 up to 28. Okay, so itest natin ngayon yung mga prime divisors. Let's start sa smallest. So surely 2 does not divide 831 kasi 831 is odd. So ang tanong, yung susunod ba na prime divisor na? So kung titignan natin yung 831, does anybody know how to get alam nyo ba yung divisibility rule for 3? Kasi kung alam nyo, makikita nyo agad na yung ating 831, it's divisible by 3. So if not, edi let's apply yung division. So meron kang 2, 6, 7, So tama nga, yung ating 3, it divides 831. Okay, so divisibility rule, pupuntahan natin to later sa chapter 4. Sa divisibility rule for 3, if the sum of the digits is divisible by 3, then the original number is divisible by 3. So getting the sum of the digits of 831, 12 yung result, and 3 divides 12. Okay, so since yung ating, since nagkaroon tayo, nakakita tayo ng divisor ni 831, 831 is not prime. So although yung intention natin ay magamit yung contrapositive ng 3.5.1, still, nakuha natin o we were able to arrive at a correct conclusion that 831 is composite. Okay? Gamitin ulit natin this time to test if 277 is it prime. So dapat kung yan ay composite, meron siyang divisor prime divisor na mas maliit kay 16. So ano ba ang mga primes na mas maliit sa 16? So konti lang naman yon. 2, 3, 5, 7, 11, 13. So ititest natin yung mga yon, meron ba sa kanilang magde-divide kay 277. So if we are to check, dito na natin i-check. So yung 2, of course, it's not a divisor of 277 kasi prime si 200, odd si 277. Yung 3, hindi rin niya i-divide si 277 because the sum of the digits, it's not divisible by 3. So proceed tayo sa 5, hindi rin siya divisible by 5 kasi any multiple of 5 will either end with 0 o kaya with 5. Okay, so hindi divisible by 2, 3, 5. Ang sunod natin na prime ay 7. So 277, divide mo by 7. Hindi siya magbibigay ng integer. So it's not divisible by 7. Sunod ay 11. Again, hindi magbibigay ng integer. Sunod ay 13. Oopsie. So, sunod ay 13, hindi pa rin magbibigay ng integer as r 3.5.1. Sigurado tayo na yung end natin ay prime. So, among the prime integers that is smaller than square root of 277, walang magdi-divide kay 277. Kaya, yung 277, it's prime. Okay, so that's how we use, kung hindi man sa sieve of Eratosthenes, that's how we use our theorem 3.5.1. Okay, so on its own, pwede mo i-consider as a primality test. Okay? So etong part na to, iwan ko sa inyo. So basically, ang binibigay dito ay n consecutive composite integers. So it's similar to a sequence generated in the last section, yung 3.5.6. Pero dito, ang generate naman na sequence, so not necessarily consecutive, but it's an arithmetic progression as well. But this time, it's an arithmetic progression of primes. Okay, so dito, arithmetic progression of primes sa 3.6. Tapos dito ay arithmetic progression of composite integers. Okay? So, iwan ko na yung Theorem 3.5.2 sa inyo. So, ang gusto kong tignan ay so, magpapalit lang ako ng share. Sabi ko nga pala, magsisingit ako ng deterministic. Probabilistic. Okay. So, singit muna natin yung probabilistic na primality test. Yung example ng probabilistic primality test ay yung nandito sa page 15 ng module nyo. So, ang tawag dito ay primality test because it's based on a problem proposed by Fermat. So, kilala nyo tama si Pierre de Fermat? So, Pierre de Fermat, it's a lawyer by profession, pero mathematician siya during yung pastime niya, it's math. And known siya, he's very well known for proposing a problem and stating na may proof siya, pero hindi niya napapakita yung proof. Okay, so kung familiar kayo sa Fermat last theorem, so yung Fermat last theorem, ganun din yung scenario. Nagsulat siya sa libro, nag-note siya, sabi niya ay, na-proof ko na to, wala tong solution for n greater than 2, but space is not enough to show the proof. Okay, so other than the Fermat last theorem, meron tayong tinatawag na Fermat little theorem. So, i-discuss natin tong Fermat little theorem pagdating ng chapter 4. So, ang sabi ng Fermat little theorem, ang sabi niya, nagsulat, meron siyang sa panahon nila lagi ay may, actually kahit naman ngayon, the mathematicians write to each other for collaborations or inputs about a certain problem. So, si Fermat, sumulat siya kay Bernard. So, in 1640, he wrote to, I'm not sure sa pronunciation, so Bernard de Bessy. Nagsulat siya kay Bessy. Ang sabi niya, so ito ay okay. So, ang sabi niya sa letter, ang result daw, kapag yung a to the p minus a ay dinivide mo by p, yung a kahit ano, yung p dapat prime. Okay, so pag dinivide mo yan by, lagi yan divisible by p. So, si a to the p minus a ay laging divisible by p. So, if we are to use our notation sa chapter 4 kasi, titingin tayo kung ano ang remainder. So, when we say a to the p minus p has no remainder, has zero remainder when divided by p, we write it in this manner. Okay? So, kapag ito, dinivide mo by p, ang remainder ay 0. Okay? So, yan yung notation natin na titignan sa susunod. Okay? So, ang tanong ay, paano kapag ang sabi niya, ito daw ay totoo, pero hindi niya nabigay yung proof. Meron daw siyang proof, pero hindi niya nabigay. So, ito, 1640. Okay? Pero, later pa, nabigay yung proof by a different mathematician. So, si Euler in particular, nagbigay ng unang proof. Isa sa mga nagbigay ng unang proof for the Fermat little theorem. Okay, so anong gagawin natin dito sa Fermat little theorem? Ang tanongin natin ay paano kapag hindi prime si P? Totoo pa rin ba na kapag meron kang a to the p minus a, ay multiple pa rin siya ni p. So, si a to the, kung n yan, si a to the n minus a, siya ba ay multiple pa rin ni n? Okay, so dito, let's look at the expression instead of looking at a to the n minus a. Tignan natin kapag meron kang a to the n minus 1, minus 1. Okay, so ito pareho lang naman eh. So dito sa Fermat primality test, instead na ito yung titignan natin, dito na lang tayo titingin. Kasi kung i-compare natin si n at saka si a, edi either relatively prime sila o hindi sila relatively prime. Kumbaga, isang number lang yan eh. Matitest mo na agad kung meron niya, kung yung n mo i-divide si a eh. Okay, so dito na lang tayo tumingin. Okay, so ang sabi ng ating Fermat primality test, if we are to input n, yung n yung hinahanap, inaalam natin kung prime or composite. Tapos yung k natin ay kung ilang beses tayo magpipili nung base. Kasi yung a, any integer. So yung k, ilang beses tayo pipili nung base. Okay? Kapag yung n, hindi dinivide itong buong to, sigurado tayo na composite yan. Okay, so for the proof and for the proof of FLT, titignan natin to sa chapter 4. So, kung yung n natin hindi dinidivide to, sigurado tayo that n is composite. Okay? Tapos, kapag yung n natin i-divide to, ang gagawin natin ay uulitin niya yung process. Bakit uulitin yung process? Uulitin niya yung process kasi hindi ka pa sure kung siya ay prime or composite. If it divides, hindi ka pa sure kung it divides or composite. Therefore, for higher probability, ititest mo pa ng ititest kung yung iyong itong expression na ito ay divisible na by n. So, I'll give you an example. So, for example kasi, meron kang, siguro tingin tayo dito, para maliit. Kasi pag dito tayo titingin, baka, for an illustration, it would require us to provide a large number of a or of n. So, para maliit yung illustration natin, maliit yung a at saka yung n natin, dito tayo tumingin. So, for example, meron kang 6. So, maliit lang. Ititest mo kung yung 6 mo ay prime or composite. So, randomly, pipili tayo ng base from 2 hanggang 4. Okay, so, suppose ang napili natin ay 3. So, si 3 raised to 6 minus 3, so ito ay equal saan? So, meron tayong 3 raised to 6 minus 3. 3. So, 726. So, ito ay 726. Tapos, makikita natin na kapag dinivide natin yan by 6, we get 1, 6, 12, 2, 1. Divisible siya by 6. So, hindi porke yung n mo, dinivide niya ito, ay prime na siya. So, hindi porke yung n mo, i-divide ito, prime na yung meron ka. Okay, so it might be prime. Hindi ka pa sure eh, it might be prime. Okay, so, kung pipiliin naman natin, imbis na 3 yung base, ay hindi 3. So, kunwari 6. 2 to the 6 minus 2. So, this is 30. Sorry. 2 to the 5. So, meron kang 62. So, yung 6, this time, hindi na niya dinivide si 62. Therefore, after choosing another base, sigurado ka na yung n mo ay composite. Okay? Paano kapag, so ano pa ang pwede? 4. Pwede 4. So, kung 4 to the 6 minus 4. So, saan to equal? 4 to the 6 minus 4. Okay, so ito ay i-divide ng 6. Okay? So kapag yung pinili nating beses, kung kailan tayo, ilang beses natin to i-check, isa lang. Tapos nagkataon na ang napili natin ay 3 na base o kaya 4 na base. Ang mangyayari ay hindi ka pa sure kung composite o hindi. Pero kung after one trial, A was chosen to be 2, sigurado ka na composite siya. Okay? Kasi, kaya probabilistic kasi there are some cases wherein you do not have a precise conclusion. Okay? So, hindi ka pa sure kung composite o hindi. Okay? Para mas malaki yung chance, para mas malaki yung probability na tama yung conclusion mo, ay didamihan mo ng beses sa pagpipili ng A. Okay? So, if ever there are composite numbers that divides this. For example, yung 6, it's a composite number pero dinidivide niya to when A is equal to 3. We call 6 a pseudoprime. To be more specific, that's a Fermat pseudoprime. And we call 3 a liar. Okay, so pseudoprime kasi sa proseso na ito, na sundan niya or yung behavior ng prime ay similar sa kanya. Okay, so kapag prime si P divides this. Okay, so dito n, although hindi siya prime, it still divides this. So similar yung property nila, pero yung n hindi prime. So siya ay pseudo-prime. So may tanong ba dun sa ating dalawang primality test, Fermat at saka yung ating sieve? Or Theorem 3.5.1? Okay, so punta na tayo dun sa last theorem nga, nasa section 3.5, yung prime number theorem. So in the prime number theorem, meron kang function pi. Okay, so meron kang function pi. So yung pi na function na ito ay pangalan lang ng function ha. So wala yan kinalaman sa pi number. So yung ating pi of x, it gives us the number of primes from 1 to x. So for example, doon sa ating 1 to 10. Ilipat ulit ako. So sige, kung ang x natin ay, so if our x is 10, ilang prime numbers from 1 to 10? So we know that 2 is prime, 3, 5, and 7. So ang pi of 10 would be 4. Kung meron kang x na 20, meron kang, in addition to this prime, meron tayong 11, 13, 17, at saka 19. So, meron kang 8 na prime from 1 to 20. So, ang pi of 20, it's 8. Nung tayo ay nag-sieve of Eratosthenes, up to 200 yung tinignan natin. So from that list, bibilangin natin yung ilan yung prime numbers from 1 to 100 and verify that's 25. So meron akong table dito. Kung ang x natin ay 1,000, so from 1 hanggang 1,000, meron tayong exactly 168 primes. So from 1 to 10,000, we have exactly 1,229 primes. Okay, so kapag kasi tayo ay so the purpose of the primality test is to identify if one number is it prime or composite. So, kung maghahanap kasi tayo ng prime, ang tanong, as the integer increases, ano kaya yung probability na prime siya? Kasi kung probabilistic, 'di ba, primality test. Kung meron kang malaking integer, ano kaya yung kung meron kang integer, the nth integer, and the n plus 1 integer, gaano kalayo yung integer, prime integers na iyon? Okay, so, gaano kalayo kaya yung isang prime sa susunod na prime sa kanya? So, kumbaga, ang pinupunto ko dito, ano kaya yung distribution ng primes? As the number increases, will the primes get, mas dadami ba yung primes? O mas lalapit ba yung prime sa isa't isa? Okay, so dito, dinescribe or it was proposed by Gauss nung 15 years old lang siya, that the distribution of the prime of this function, it's asymptotically equal to x over ln of x. So, anong ibig sabihin yan? Anong ibig sabihin ng asymptotically equal to? So, in practice, pwede natin yung tignan as roughly approximately equal to. So, roughly approximately equal to. Pero, tignan natin kung ano yung difference ng asymptotically equal sa roughly approximately equal. So, kapag sinabi nating approximately equal, if the value of x is large, the rough difference between the two quantities are close. Maliit yung rough difference nila. As x increases, gumaganda yung approximation kapag gumaganda yung approximation. Pero kung titignan natin yung difference between pi of x and x over ln of x, ano yung makikita natin? Magsimula tayo sa 1,000. Ito ay 168. Exact number of primes na mas maliit sa 1,000. Ito ay approximate value of x over ln of x. 144 yan. Yung ating difference, exact difference, hindi exact kasi approximate to. So the approximate difference of these two quantities, that's ilan? 24. Approximately 24. Dito naman, susulat natin. Dito naman, ang difference natin ay approximately 100. So, sulat natin, roughly 100. So, susunod, ang difference natin ay approximately 900. So, kung tutuloy pa tayo, it doesn't seem like the approximate difference between these two quantities gets smaller. Okay, so what exactly do we mean by asymptotically equal then? Anong ibig sabihin yan? Kung yung brute difference, approximate difference between the two quantities, hindi naman lumiliit as x increases. So, in value, yung magnitude nila may not be close, but their ratio gets closer to 1. Okay, so yun yung ibig sabihin natin ng asymptotically equal. Their ratio gets close to 1. Okay, so the limit as x increases approaches 1. Okay, so ito yung value ng pi, ito yung approximate ha. Dito, puro approximate value of x over ln of x. So, nagsimula tayo sa 1.16, 1.32, 1.1. So, paliit ng paliit yung ating ratio. And it approaches 1. So, it approaches 1. So, in practice, although we can use this quantity to roughly estimate pi of x, what we mean by approximately equal, it's more than just a rough approximation. Okay, so siya ay, yung ratio nila ay mag-a-approach sa 1. Okay, so ano ngayon kung ang ratio nila mag-a-approach sa 1? Okay, so ano ngayon kung ang ratio mag-a-approach sa 1? So, pag sinabi nating ratio na yan, we can actually look at the relative size of pi of x. So, di ba, pag sinabi nating pi of x, binibilang niya yung prime numbers from 1 to x. So, ano yung density na gaano karaming primes from 1 to x? Masulat ko. Pag sinabi kong relative size of pi of x among the x integers from 1 to x, ilan yung prime? Okay? So dito, ang gawin natin, x over ln ng x times 1 over n din. Okay? So ito yung relative size of pi over x. Tapos ito, yung ating relative size din ng ratio x over ln of x. So, it captures, so since 1 yan, it captures the idea that when you're looking at densities or relative sizes, it's a good approximation. So, 1 is a good approximation for the other. So, kung meron kang kung meron kang large enough x, tapos pipiliin mo, aalamin mo na in interval. Specifically muna I want to x. In an interval whose length is x. So yung number ng elements dito sa interval ay x. The probability that 1 is prime, it's roughly pi x over x. Okay, so yun yung kinakapture ng ating prime number theorem. Hindi sa ito ay malapit yung value magnitude-wise dito, kung hindi, ang sinasabi niya yung relative sizes in a group of x integers. Roughly, isa sa kanila ay may probability na ganito for it to be prime. Okay, naiintindihan ba? So maganda, sobrang laki ng impact ng prime number theorem kasi nga sabi natin ay gusto natin malaman kung prime yung isang number o hindi. Tapos gusto natin malaman ay ano yung chances maging prime siya o hindi siya prime. Okay, so as malaking tulong to, especially for those who are trying to decrypt or to destroy known RSA, yung mga crypto systems that relies on the difficulty of determining the prime factorization of a very large number. So, sobrang laki ng importansya ng prime number theorem. So, again, the prime number theorem captures the idea that the relative size of pi of x, it's equal or approximately equal to the relative size of x over ln of x. Okay, so meron akong sinabi dito about the prime number theorem na meron tayong elementary proof. Kasi originally, na-proof siya ni So, na-proof siya independently by Adamard and I'm not sure kung paano to i-pronounce. So, silang dalawa independently came up with a proof for the prime number theorem. But the proof relies heavily on complex analysis. Okay, so complex analysis. And as we know, kahit na may mga theorems kahit na may mga results na, may proof na siya, mathematicians often find ways to have a simpler approach or a simpler proof. So sabi ang usual na tanong ay kapag in-state mo yung prime number theorem, there's no mention about complex analysis eh. Kasi pwedeng real analysis lang to kasi yung x mo real number naman eh. So saan pumasok yung complex analysis? Medyo hindi halata kung saan siya papasok. So the challenge was after proving using complex analysis. Meron kaya siyang proof na hindi nagre-require ng complex analysis. So sabi nga natin in general, pag hindi nagre-require ng complex analysis, we call them elementary. So meron bang elementary proof yung prime number theorem? So a very well-known mathematician, so si G.H. Hardy, I'm not sure kung nilagay ko or sinite ko yung biography niya at the end of our module, but G.H. Hardy is very well known as a number theorist. And so yung gawa niya, yung mga publications niya, usually sa number theory at saka sa mathematical analysis. At very well known siya for mentoring Ramanujan. Okay, so si Ramanujan ay number theorist din at may results din siya sa mathematical analysis. So sabi ni G.H. Hardy noong 1921 na yung elementary proof daw ng prime number theorem, it's extraordinarily unlikely. So hindi lang very unlikely, it's extraordinarily unlikely. So it's a challenge to the mathematical community to come up with a proof for the prime number theorem that does not require complex analysis. So after some time, so 1921 yun. So after some times, noong 1949, actually in some references, 1948. So around 1940s, may mathematician, so si Selberg, came up with an elementary proof. So sobrang laki ng impact niya dun sa community, mathematical community, to the point that he was given a Fields Medal. So may tanong ba sa prime number theorem? Ano yung sinasabi ng prime number theorem? Bakit kailangan natin tingnan yung prime number theorem? Ano yung kinagandahan ng prime number theorem? Wala? Okay, so dito naglista ako ng 4 na mga, kasi yung prime number theorem ay, so matagal siya na-propose. Pero na-prove siya after more than almost 100 years. So maraming mga problem na open problem siya for quite some time. Tapos na-resolve after say 100, yung Fermat last theorem after almost 400 years. Pero there are some problems that are yet to be shown. Okay, so hindi pa sure kung siya ay totoo o hindi totoo. So examples of these problems are the so ang tawag dito ay nasulat ko ba? Hindi. So these are examples. Itong apat na to in particular are called the Landau problems. These are well-known open problems in or unresolved problems in number theory. So basahin niyo yung 1 to 4. So gusto kong idagdag yung number 5, yung Goldbach's conjecture. So the Goldbach conjecture, nakasulat siya actually doon sa list of possible topics ninyo. Hindi possible, kundi suggested topic sa inyong project. So, ang sinasabi sa Goldbach conjecture, the current statement of the Goldbach conjecture is that if you have an even integer greater than or equal sa 4, it can be written as a sum of 2 primes. Okay, so for example, ito chinek ko, 2022. It can be written as a sum of 43, that's prime, and 1,979, so that's also prime. Okay? Yung ating, start tayo sa maliit, o 103, chinek ko na rin to. So alam natin 103 is prime, 101 is prime, and it can be written as a sum of 2 and 102. So yun yung illustration, dalawang illustration lang for this statement. Okay, but the original statement of Goldbach's conjecture, so this was proposed by Goldbach. So yung original statement niya, it's a ternary problem in the sense na it's a sum of 3 primes. So ang sabi niya, every integer greater than 2 can be written so yung original, every integer greater than 2 can be written as a sum of 3 prime. So bakit biglang nagbago? Yung original ay every integer, it seems like it's stronger. It's a stronger version. So dito, yung current statement na, it's an even integer. So take note, sabi ko last time, pahapyaw ho minention, at some point in time, 1 was considered a prime. And so when this original problem was proposed, 1 was still considered as prime. And so for example, yung 3, kaya mo daw siya isulat as a sum of 3 primes. 1 plus 1 plus 1. Okay, so yung 2022, it can be written as a sum of 3 primes. 2, 41, 1979. Okay, yung 4, kaya isulat as a sum of 3 primes. 1 plus 1 plus 2. Okay, kasi ulit, back then, 1 was considered as a prime. Thus, since today, we do not consider 1 as a prime, a restatement of the original problem needs to be done. So, ito na yung restatement niya. Ano pa? Tanong? So, kung wala nang tanong tungkol sa prime number theorem, proceed tayo dun sa next section. So, sa next sections pa ng chapter 3, tayo ay mag-number theoretic functions or arithmetic functions. Tapos, titingin tayo ng greatest integer function. So, yung greatest integer function, it's not an example of, na-miss ko. It's not an example of an arithmetic function. Pero, nilagay ko pa rin siya dito o sinunod ko sila kasi gusto kong balikan yung ating division algorithm. Okay, so 2 sections na lang bale yung i-discuss natin. Yung 3 sections, yung 3.2, yung 3.3 kasi it's a property of arithmetic functions. Tapos yung 3.4 ay tungkol sa greatest integer functions. So yung 3.6, ginawa kong optional, hindi kasama sa problem set. So we have two topics left, two main topics left for chapter 3 bale. Yung arithmetic functions natin at saka yung greatest integer function. So ano yung gusto nating tignan sa mga arithmetic function? So of course, we need to define examples and properties. Ano yung properties? Kasi kailangan natin isang example ng arithmetic function na titignan natin ay kailangan natin sa chapter 4. So, what do we mean by a arithmetic function? So, pag sabing arithmetic function, it's simply a function defined on the set of positive integers. So, kung pwede kang, kunwari sequences, we know that sequences, yung domain of definition mo ay set of positive integers din. O kaya minsan, set of whole numbers. Okay, so similar yung ating arithmetic function doon. Okay, so yung domain of the definition or the restricted domain of the function is the set of positive integers. So for example, if we have an f defined to be, so yung defined to be 1. Okay, so i-restrict natin na yung n natin is a positive integer. And we are to map n to 1. So napaka simple lang, pero it's an example of an arithmetic function because of the restriction that it's n is a positive integer. Okay, so i-restrict mo, yung domain mo ay positive integer. So kung meron kang f of n equal sa n squared, i-restrict mo din na yung n mo ay positive integer. So itong mga to ay example ng arithmetic function. But these functions, yung behavior niya, ay pwede natin siyang, pwede siya mag-hitch sa function that has a larger domain. So for example, yung ating function without the restriction, that n is a positive integer, f of x equals sa x squared. Alam na natin kung anong behavior niyan parabolic. Okay, so the idea here is these types of function, makikihitch siya dun sa behavior ng f of x equals sa x squared. So ang pinupunto ko dito, itong mga class, these are arithmetic function, but they're not that interesting because we already know how to look at the behavior of this function by looking at quotation marks, larger functions. Okay? So, ang gusto nating tignan ay mga arithmetic functions na has a more interesting behavior na possibly hindi katulad ng isa na meron na tayong agad paraan paano i-compare siya to a continuous function. Okay, so itong mga functions na ito ay titignan din natin kung ano ang property. Specifically, are they multiplicative? So, dun sa pangalan na multiplicative, you might think that multiplicative functions are functions such that, so integer, restrict na natin, integer, gamitin natin si mn. So, si f of m, f of n. So, sa pangalan, may term ka na multiplicative. Baka isipin natin na pag sinabing multiplicative, totoo to. Okay, so, wala naman problema dito. So, ang ganitong function na yung mga function na magsasatisfy nito, we call it completely multiplicative. So, it turns out it's a very strong property of arithmetic functions. Okay, so other than completely multiplicative functions, titignan din natin yung a less strong property na multiplicative yung function. So, ito ay totoo whenever m and n, yung GCD nila ay 1. So, whenever relatively prime si m at n. So, ito tawagin nating multiplicative functions. Functions that satisfies this, we call it multiplicative function. So, special case lang siya nito kasi dito wala tayong sinabi kung may common factor. May common factor ba si M at saka si N? Okay? So, yun yung titignan nating property pagdating sa susunod na section. Okay, so nagbigay na ako dito na examples ng arithmetic function. Yung una, tinawag nating tau. So yung tau natin, that's the number of positive divisors of n. So dito, kapag gagamitin natin yung tau at saka yung sigma, let's restrict that d, the divisor of n, it's positive. Yung d, divisor of n, ay positive. So, bale, ang binibilang lang natin sa tau ha, ay positive divisors. Ilang positive divisors meron siya. So, ito, counter lang. So, kaya 1 yan, kasi it's a counter. Once meron ka ng d that divides n, yung count mo, dadagdagan mo ng 1. Okay? For sigma, bukod sa yung sigma, ang gusto natin ay sum na ng mga divisors. Kaya dito, the representation of the divisor d, it's d itself. Ang ina-add mo ay yung d mismo. Dito, ina-add mo, ang kino-consider mo ay count of the... So dito ay meron kang counter for the number of positive divisors. Ito ay sum na ng divisors. Okay, so for tau and for sigma, ito yung formula na gagamitin natin. So given the canonical form or the canonical prime factorization of n, we can compute tau as a product of these quantities. Tapos yung sigma, ito din. So ang gawin natin ay gamit yung theorem 3.2.4, yung ating tau ba at saka sigma ay completely, siya ba ay multiplicative? Yun muna, multiplicative. Kapag multiplicative kasi, magsisimula tayo sa factors na relatively prime. So, kung yung n natin, i-decompose natin such that yung unang factor walang common sa pangalawa, dapat hindi natin paghihiwalayin yung factor. So, for example, meron tayong p sub 2 raised to k sub 2. Hindi pwedeng hahatiin natin yung p sub 2, yung bilang ng p sub 2. So, ito ay r sub 1, r sub 2 kunwari. Ito ay yung unang factor, ito yung pangalawang factor. Para magsimula tayo sa relatively prime na divisors of n, hindi pwedeng yung prime natin, paghihiwalayin natin kung ilan beses siya nag-appear. So, dito, meron kang multiplicity lang of r sub 1. Dito, may multiplicity ka of p sub 2 na r sub 2. So, hindi pwede yon kasi meron na tayong common na p sub 2. So, to start with relatively prime divisors of n, dapat hatiin natin yung primes natin. Hindi natin paghihiwalayin yung primes. Hahatiin natin precisely so, hindi natin hahatiin yung k sub 2. Ang hahatiin natin ay yung mga p sub i's. Okay, so kung si p sub 1 nasa una na, hindi na sa pangalawa. So, kung meron kang apat na lang muna ha. So, suppose this is our m sub 1. This is our m sub 2. So, kung kukunin natin yung tau of m sub 1, ito ay k1 plus 1, k2 plus 1. Pero yung tau for m sub 2, it's k sub 3 plus 1, oopsie, 3, 4. K sub 3 plus 1, K sub 4 plus 1. Okay? So, ang mangyayari, pag kinuha natin yung product niya, ito mismo yung makukuha natin. That's the tau of n. So, it's very clear, based on the prime factorization, that tau would be multiplicative. Okay? Similarly, kung meron kang sigma, kung yung first two ay magiging sigma of m sub 1, all the rest ay manggagaling sa sigma of m sub 2. Madali din ipakita na yung sigma natin ay multiplicative. So with the prime factorization and with these two formulas, madali ipakita na multiplicative yung dalawang yan. Okay, so tignan natin itong 24. Nandito na pala. So, complete, siya ay multiplicative, pero hindi sila completely multiplicative. So, an example would be by looking at 624. So, 624 can be decomposed as a product of not relatively prime integers 24 and 26. And it turns out, using the formula, the two quantities are not equal. So, using the formulas, these two quantities are not equal. So, si tau at si sigma, kahit na multiplicative siya, hindi siya completely multiplicative. Okay? So, ang gusto kong tignan ay paano kapag meron tayong arithmetic function na kung saan hindi siya multiplicative, instead, it's additive. Okay, so instead, it's additive. So suppose meron tayong function f, and it's said to be additive. So what this means is, f of m, n, that's equal to f of m plus f of m. Okay, whenever so additive yung arithmetic function f, anong ibig sabihin? So definition yan, pag kinuha daw natin yung f of mn, it's the sum of the two function values. So ulit, whenever mn are relatively prime. So bakit maganda tignan din? So yung goal natin for this section ay pag-aralan yung Euler-Tauschent function. Gagamitin natin to pagdating ng chapter 4. So the Euler-Tauschent function, it's multiplicative. Okay, so it's multiplicative. Kaya ang major sections, yung additional property na tinignan ko ay para sa multiplicative arithmetic function. So gusto kong tignan yung mga additive functions na hindi multiplicative kasi pwede pa rin naman natin siya ma-relate sa multiplicative function. Okay, so maganda kasi yung properties ng multiplicative function. So if ever a function it's not multiplicative, maganda na i-relate siya sa multiplicative functions. So let's consider the function defined to be the number of, so let's define omega of n as the number of distinct prime divisors of n. So, magbibilang ka lang ng distinct prime divisors. Okay, doon kasi sa ating tao, nagbibilang ka ng distinct prime divisors, pero sinasama mo pa yung ibang composite na divisors. So, kung ang titignan lang natin ay prime divisors of n, we call it omega, yung omega function, Wn. So, kung meron tayong 2, so maliit lang muna, 2. Of course, the number of prime divisors, it's just 1. Meron kang 4. So, ito ay, yung 4 kasi natin, it's 2 times 2. So, meron ka dito na 1. Ano lang 1 copy of 2. Meron kang 6. So, ito ay 2 times 3. So, that's 2. Okay, so binibilang mo lang yung prime divisors, distinct prime divisors. So, if in general, n has a canonical prime factorization of this form, R. Then, omega of n would be, so bibilangin mo lang lahat ng distinct primes, isang counter dito, isang counter doon. So, meron ka lang R. Okay? Okay, so tingnan natin itong, so dapat pala sinulat ko din yung omega of 3. Omega of 3 only has 1 prime divisor itself. So, 1 yan. So, dito, we can notice that 2, it's a sum of 1 and 1. So, it's the sum of omega 2 plus omega 3. Okay, so this is an illustration that the omega of n, it's a additive. It's an additive function. Okay, so dito din, mahalata natin, madali mapakita na additive functions yan. Kasi kung magsisimula tayo sa relative prime, hahatiin natin yung primes natin. So, kung meron kang primes P1 hanggang P sub R, P sub S, tapos sa susunod na koleksyon, meron kang primes P sub S hanggang P sub R. So, dito we have S primes. Dito meron tayong R minus S plus 1 primes. So, kapag kukunin natin yung omega of n, this is R, pero pag kukunin natin yung omega of M1, that's S. Tapos yung omega of M sub 2 would be R minus S. Meron ba akong... okay. Plus 1 kasi. Hindi dapat... Magsisimula dapat tayo sa relatively prime eh. So, kung magtatapos yung M sub 1 as a collection of the product, as the product of all primes, of all factors of the form P1 to the K1 hanggang P to the SK sub S, dapat yung susunod na prime, hindi sila pareho. Okay, so ito ay K sub S plus 1, ito ay K sub R. So kung ito si M1, ito si M2, yung bilang ng distinct primes ni M sub 1 ay S, yung bilang ng distinct primes ni M sub 2 ay R minus S. So ito ay equal sa S plus R minus S. That's omega of M1 plus omega of M sub 2. Okay, so using the canonical prime factorization, totoo nga na yung omega natin ay additive. Tingin pa tayo, ano ngayon kung additive yung function? Let's end there. So, ano ngayon kung additive? So, kapag additive yung function, so let's recall a function, the exponential function. So, meron kang e to the, so meron tayong e to the m times n plus n. Okay, so if sa exponential function, kung yung n natin kaya i-decompose as a sum of two integers m1 and m2, we know that this, by rules of exponent, this can be rewritten in the form e to the m1 raised to e to the m2. So rules of exponent, alam natin to. Okay, so rules of exponent. And so ang mangyayari if we have a function that is additive, so additive CF. So kung additive yung ating arithmetic function f, ito ay equal doon. M1 and M2 are relatively prime and their product is n. Tapos rules of exponent, ito ay equal doon. So kung titignan lang natin, ito papunta doon. If we started with relatively prime M1 and M2, it turns out that the exponential function raised to an arithmetic additive, sa exponential function raised to an additive function, it's multiplicative. Okay, so kahit na itong omega ay hindi multiplicative, we can, because it is additive, we can come up with an arithmetic function that is multiplicative and is based on omega. Okay, so bale, sa susunod na meeting, multiplicative functions na yung focus natin. Tanong? Okay, meron na nag-type ng P, isa na lang hindi. So, paki-type P tapos you can go, see you next week.